Hello everyone, my name is Huang, a second-year PhD candidate at the University of South Australia. Thank you for offering me this opportunity to present the topic of a framework for designing and optimizing LC3 cement, considering the mechanical, environmental, and financial properties. Let me introduce some background information of the topic. Concrete is an essential material we needed to house people to build roads, bridges, and tunnels. Based on the previous study, concrete makes us more than 50% of building material in Australia. Concrete is therefore the second most used material on Earth. And Portland cement is the basic binding material for concrete. For this reason, cement has a significant environmental impact, and the production of Portland cement accounts for around 7% of industrial energy consumption and 9% of CO2 emission annually. So if we can't do without it, but we can reduce the carbon footprint. The most effective strategy to reduce the emission of cement manufacturing is the utilization of supplementary cementitious material to achieve a partial clinker replacement. The most common cement substitutes are the reactive byproduct from other industries such as slag and fly ash. And today, these two materials account for around 15% of cement production. The slag availability has decreased from 70% of cement production in 1980 to only 8% in 2014. And the quality of fly ash is variable, and only 1/3 of fly is suitable for using cement. So if you look at everything else we have, but in quantity we need clay and limestone. The clay we need can be calcined and produce a reactive phase called metal kaolin, which has previously been used in SCM. But the energy-consuming process of calcined clay made the economy of clay substitution marginal. This has led to a potential solution to reduce carbon emission by substituting cement with both limestone and calcined clay. So it's a so-called LC3 cement. So what is LC3 cement? It's a recently developed ternary blend cement that combines calcined clay, limestone with addition of gypsum, offering an equivalent of performance to OPC in terms of strength and durability. In recent years, enormous efforts has been made to investigate the factor affecting the strength performance of LC3 to determine the optimal formulation of LC3 cement, such as clinker composition, clinker content, kaolin content of clay, clay calcination temperature, calcined clay to limestone ratio, and so on. So when designing the LC3 mixture, a benchmark factor to consider is fundamental mechanical properties and compressive strength. However, traditional binder design involves preparing trial batches and selecting the mix that meet the design requirements, which can be time-consuming and require extensive experimental programs. In addition, sustainable practice and costs associated with LC3 cement are also vital. And this process becomes more complex for ternary blend cement like LC3, as the properties are influenced by a broader range of factors and interactions. So how can we improve the design process of LC3 system? By considering the mechanical and environmental performance, material costs, computational optimization frameworks were developed in this study to streamline the LC3 mixture formulations, reducing laborious and time-consuming experimental testing. So the LC3 cement binder design frameworks comprise a four-step process. Firstly, multivariate polynomial regression models were imported to model compressive strength of LC3 mixture. Secondly, the CO2 equivalent was calculated by using a developed life cycle assessment model, alongside with the collection of material costs of average market price of LC3 material to facilitate the cost evaluations. So after these three objective functions were determined, the Gubi optimizer with weighted sum method was utilized to identify all the Pareto optimal solutions. Finally, the Pareto optimal solution were ranked using a technique called TPSIS to give a weight of the Pareto solution and leading to the final selection for the optimal LC3 mixture. So before the application of the framework, 10 critical factors of LC3 are determined based on the previous study, and as shown here, including the mass of the calcined mix of calcined clay, limestone powder, gypsum, and Portland cement. The content of sand, water, and super plasticizer are also included. And the calcined content of calcined clay, calcination temperatures of clay, and the current age of the sample. To ensure the collection, the quality of data, the following conditions shown also on the right-hand side were considered for data acquisitions. Therefore, a data set consisting of 360 samples were established from the literature. The static analysis and data distribution of the input, which is the 10 impacting factors, and the output, which is the compressive strength, is shown here. So how do we model the relationship between these 10 impacting factors and the compressive strength? In this study, a regularized multivariate polynomial regression model was employed to predict the strength performance of the LC3 mixture by establishing a nonlinear relationship between the input impacting factor of LC3 cement and the output, which is compressive strength. So NPR model is a type of regression analysis that can model the complex nonlinear relationship between an output variable and one or more input variable in a high degree polynomial functions. The detailed procedure for construct the NPR model is shown here. The dataset used for the NPR model was randomly divided into two subsets, the training set and the testing set, with a portion of 70% and 30%. The data in the training set is used to establish the predict model, while the testing set is used to verify the model performance. So to ensure the accuracy of the model, the performance of the predict model is evaluated through three mathematical indicators shown on the bottom left-hand side, which is the R-squared value, and there are mean absolute errors and the root mean square errors. So how can we verify the accuracy of the model? The predict model compared with the predict model from the NPR model compared with the experimental result from the collected literature, and the arrow bar showing on the testing set and the training set is shown on the top two figure. Below is the in addition the mathematical indicator, the R-squared value, MAE, and R and SE value indicator shown on the bottom two figure, and all these results give a fairly reliable results by showing a decidable fitting of the data. Following next is the environmental impact, specifically the associated carbon emission of LC3 productions. In this study, we employed the life cycle assessment approach, which is a systematic method to evaluate the potential environmental impact of a product through its life cycle. And the LC3 model using this study following the ISO guideline, which consider 4 major steps, including the goal and scope definitions, the inventory analysis, the impact assessment, and finally the result interpretations. The first is the goal and scope definition, which describe the model purpose and define the system boundary. The LCA model system boundary consider a cathode to gate scenario, covering from the manufacture stage from raw material extraction to LC3 cement productions, as shown here. So this process includes the raw material of LC3 cement extraction, raw material binding, grinding, and power processing, and the clinker cooling, finish milling, and grinding, material conveying within cement plants, the aggregate productions, and admixture productions. However, the concrete manufacture, like the cement manufacture, including batching, casting, and clearing, demolition, disposal, is not considered in the cathode to gate system boundary. So in addition, unlike other byproducts from in the industry, such as fire ash and slag, which can be obtained from the plant, calcined clay used in the LC3 requires thermal activations, and this process similar to Portland cement productions, but the calcination temperature requirements comparatively low. For the inventory analysis consists of data collections, calculation of the global warming potential measured by the CO2 equivalent, and the model assumption of the LCA model. And the following table summarizes the assumption and technology used for LC3 cement productions, considering the average emission scenario. The material transportation distance considered the average case among Australia as well. And the LCA model used four major process response for emission calculations, namely the Q fuel pre-combustion and combustions, electricity consumption, and transportation of the material. In addition, non-process related, such as on-site transportation and lining with things among plants, also contribute to the emissions. So following is the Australian average electricity grid percentage and power processing field used for global warming potential calculations. So after defining the system boundary and the inventory analysis, the environmental outcome, which is the associated CO2 equivalent in kilogram for 1 kilogram of each component, can be obtained and showing here on the left-hand side. Since the calculation temperature of and clay purity can be varied in different locations, the CO2 equivalent of calcined clay production is calculated as a range. So to verify the accountability of the data, the table on the right-hand side shows the emission factors of LC3 component in recent review literature, and the results show a quite reliability of the LCA model. So after the associated CO2 and cost is determined, three objective functions are shown here for further multi-objective optimization, which means we need to find what kind of combination, what kind of value of the 10 impacting factor mentioned before align with the optimization goal. So first, a mathematical optimization called weighted sum method is used, which convert the multi-objective problem into a single objective problem by defining a scale objective function as a weighted sum of individual objectives. Therefore, the solution obtained here is called the Pareto optimal solutions. Then the Pareto optimal solution is further selected by using the TOPSIS to facilitate the final optimal scenario. So two optimization scenarios are considered in this study, which is the bi-objective optimization with minimize the compression while maximize the compression while minimize the cost, and the tri-objective optimization shown on the top table. And the Pareto optimization solution can be obtained for a range of compression from 35 MPa to 85 MPa to better illustrate the different kind of optimal combination solutions. So we're increment of 10. If you look at the data set for both by objective and tri-objective optimization, all results show a trade-off between the material cost, CO2 emission, and the compressive strength. So how can we know the best solution between this optimal solution? So we further rating this Pareto optimal solution by using the technique which is TOPSIS, and then select the optimal solution select the best solution among these optimal solutions. So this is the result we're getting for those Pareto optimal solution, right? So the optimal composition attained from the both bi and tri-objective function shown here. The result indicate it does not always follow the previous suggest ratio of 2:1 calcined clay to limestone ratio. If you look at the table A and B. So if you look at the calcined content in the graph H, which is purely being classified as the critical impacting factor of LC3 resistance, calcined clay with a lower calcined content are preference for highly substitute LC3 resistance, while higher grade clay are favorable for lower substitute LC3 resistance. So this the two main conclusion can be obtained from the optimization framework. So And last, I want to say the optimal portion of LC3 system is still a topic of debate. The developed computation framework in these presentations for LC3 mixture design gives some insight in terms of a faster and more efficient way to design the concrete mix, leading to improved performance, environmental friendly, and cost-effective concrete. Yeah, thank you.